B is asking us then about acceleration. So you're saying, oh great, I probably have to do all this over again. Actually, you don't. It's actually, we've done a lot of the hard work already. Oh, sorry, let me go back and fill in. Our magnitude is 25 and our direction is 65. Right here, we've done all this hard work to find the magnitude and direction and the x hat and the y hat of the change in velocity. And so why is part B going to be easier? It's going to be easier because acceleration is change in velocity over a change in time. So if we take this change in velocity right here and we simply divide it by a scalar, time is a scalar, it can only be positive, we're going to get a vector that's in the same direction. What I'm saying here is that the acceleration, or you might say the deceleration, but stick with me here, the acceleration here of the car is going to be in the opposite direction that it's going. So this will be easy to find because all we need to do is divide our change in velocity vectors by time and we'll have our acceleration. Let me show you down here. Okay, for acceleration, again, bear with me, I'm going to change colors here for acceleration. Let's go to some shade of blue, okay? B, we want to know what the acceleration is in magnitude, direction, and direction notation, and also unit vector notation. All right, well, our acceleration, since that is change in velocity over change in time, that means we can simply divide our velocities, whether it's in the x direction or y direction or wherever, simply divide them by time and we'll get acceleration in that direction. Here's what I mean. This is like saying our acceleration is negative 10.6 meters per second divided by, what's the time? Time is 0.34 seconds, right? Divided by 0.34 seconds x hat, all right, plus, what's our y hat? Oh, that's 22.7 meters per second divided by 0.34 seconds y hat. So let's just simplify that, and then we've gotten our acceleration in unit vector notation. Since acceleration is change in velocity over change in time, all we have to do is take 10.6 and divide it by 0.34, and we have 31.2 meters per second squared, right? Because acceleration is meters per second squared. That's the x hat direction. Plus 22.7 divided by 0.34. That's 66.8 meters per second squared in the y hat direction. That's it. That's our acceleration in unit vector notation. What did I do? I'm sorry. You're probably waiting for me to say this. What did I not do? I forgot the minus sign there, right? Yeah. This should be, I'm going to just erase this little parentheses since I have a lot of space. Negative 31.2 meters per second x hat plus this positive 66.8 meters per second squared y hat. So that's saying that there is an acceleration now in the opposite direction of travel. And if you think about it for a second, that makes sense. Because if you're slowing down, then some acceleration is acting on you in the opposite direction that you're going. It's bringing you to a stop. So the acceleration and our change in velocity are very closely related right here. And so wherever our change in velocity is pointed, that is whatever direction our change in velocity is, the acceleration is going to be in that exact same direction all the time. So wherever you have a change in velocity, there you have an acceleration. It just depends on how long it takes for the velocity to change. And that's your time. Okay, so we have our acceleration right here in unit vector notation. Easy. We can also get it pretty easily in magnitude direction notation. Again, if acceleration, a little more space here, if acceleration is change in velocity over change in time, we can simply divide the magnitude direction notation form of of change in velocity by time and get our acceleration. Here's what I mean. 25 meters per second at 65 degrees north of west. Remember, this was our change in velocity, right? Well, we're taking that and dividing it by time, 0.34 seconds. That gives us an acceleration of 25 divided by 0.34. Divided by 0.34. 73.5. 73.5 meters per second squared. In what direction? It's in the exact same direction as the change in velocity at 65 degrees north of west. This right here is our acceleration in magnitude direction notation. This is talking about the full vector right here. The unit vector notation is talking about the x component and the y component of the acceleration. And you'll see they're just like the x and the y components of the change in velocity. Why? Because acceleration and change in velocity are inextricably tied to each other. They're very closely related. They're just related by time. All right? So that was easier. It took a lot of my talking, but if you look at it, it's a heck of a lot less work than the first part. Right? We have a change in velocity. We can simply divide that by time in any form and get our acceleration. Let's do part C, which I think you'll find a lot more familiar. Part C is going to be even easier. You want to find the car's velocity after the driver hits the brakes. Velocity, the change in time is 0.17 seconds for part C. That's this right here. Okay, 0.17 seconds. So the car is not quite stopped yet. It's looks like it's halfway through the time it takes to stop. So we want to find what the final velocity is. All right, at that time. Well, if the initial velocity is 25 meters per second at 65 degrees south of east, okay, we want to find the final velocity. We don't know that. We do know the time, and we do know the acceleration. The acceleration we just found. Acceleration is 73.5 meters per second squared, which, by the way, that's a very high acceleration for a car. If you're accelerating or decelerating at that rate, you probably hit a brick wall or something, so don't ever do that. At 65 degrees north of west. So if the initial velocity, and I'm going to change back to a red right here. If the initial velocity is in this direction, that's not red. If the initial velocity is in that direction, and my acceleration, I should have kept the blue. Oh well. Acceleration is in the opposite direction. It's like we can say that the acceleration is a negative acceleration compared to the initial velocity. So it's like saying the acceleration, not the vector, but just the acceleration is negative 73.5 meters per second squared. And that's it. So look what we have right here. Time, initial velocity, solving for final velocity, and acceleration. All right, what can we do with this? Well, we can go back to our kinematics equations. This should look very familiar to you. This equation here, v final equals v initial plus acceleration times time, right? We just showed that the final velocity and the initial velocity and the acceleration are in different directions. That's why we have a negative here. But if we simply want to solve for final velocity, all we need to do is just plug and chug, really. So our initial velocity, and by the way, this is all acting in this direction right here. Sorry for that. It's acting along that axis, just the acceleration is acting against the initial velocity. So we can say the initial velocity is 25 meters per second plus our acceleration, negative 73.5 meters per second squared times time, 0.17 seconds. All right. So what's our final velocity after only 0.17 seconds? 25 plus negative 73.5 times 0.17, 12.5. 12.5 meters per second. That's our final velocity for part C after the car has only partly come to a stop. So there you go. This is our first real big problem involving change in velocity, acceleration, and time in an object moving in one direction. But if you have the concepts, or that is the principles of finding a vector's magnitude in a vector in magnitude and direction notation, as well as unit vector notation, this is all just goes back to kinematics, and it's just knowing how the vectors are related to each other in the same way that acceleration and velocity are related to each other. So I hope that helps. Come to me if you have any questions. I'll be glad to go over this with you. But for now, thanks for watching, and keep practicing.